Thank you very much. So first, a word of caution. This is not an official IPCC presentation. These are personal views on issues related to Earth's system response to 1.5 degree warming. And I would like to cover where do we stand now, what was available within the fifth assessment report of the IPCC, especially on the interface between pathways, climate response, impacts, and also a few updates on emerging knowledge and gaps. Where do we stand with respect to global warming? This is a recent update based on different sources of information. So 2015 is more than 1 degree above pre-industrial level, considering as an option the period from 1720 to 1800 as a pre-industrial reference, considering here availability of information, human influence, but also a recurrence rate of major volcanic eruptions. The trend since 1900 is between 0.9 and 1 degree Celsius, estimated by a linear regression. The trend since the 1970s is taking place at around 0.17 to 0.18 degrees per decade. When will we reach 1.5 degree for the first year? There is emerging knowledge on decadal prediction. The fact that the interdecadal Pacific Oscillation is shifting towards a positive phase suggests larger warming rates for the coming decade. So considering 1.5 degree means when, for the first time, we reach this amount of warming for 1 year. How we measure 1.5 degree warming? Is it through a linear trend, considering, for instance, 1900 as a reference? Is it when we use a running average over 30 years on a climate sense? These are options that have implications for looking at impacts and looking at pathways. I'm a paleoclimatologist, so I like to show the long-term perspective. This is the only available Holocene temperature reconstruction available. You can see that the recent centennial warming trend is getting us already ahead of the current interglacial centennial variations as we know them for now. Considering 1.5 or 2 degree warming above pre-industrial level means we may reach the mean levels on multi-millennial timescales of the last interglacial period, where we know sea level was several meters higher than today on the long term. We can also learn on the long time scale Earth system responses from the Pliocene a few million years ago. The last time the concentration of CO2 in the atmosphere was at the level of today, but sustained over tens of thousands of years. We know that human influence is clear, and most of recent warming, the last 60 years, is attributed to the warming effect of greenhouse gases, partly offset by the cooling effect of aerosols. We don't yet have an update on this attribution figure, a topic we discussed yesterday with Miles Allen. How is it possible to regularly make an update of key IPCC findings so that they keep up with the pace of change? Where do we stand with respect to human influence? Let's focus here on greenhouse gases. And what is shown here is not the usual concentration in the atmosphere. It's expressed in terms of radiative forcing, and I will use that in the rest of the presentation. And it's not the total radiative forcing, it is the growth rate. And of course, if you want to stabilize human influence, you have to have zero growth rate of radiative forcing. You can see it's not the case. In red, you have the trace gases, especially those covered by the Montreal Protocol, with a decrease in the growth rate after the 1980s. But you can see that we have a steady growth rate for N2O, an increased growth rate for methane since about a decade, and we can see also an increased growth rate of CO2 in the last decade. This is based on running averages over 3 to 5 years. Let's go back to the fifth assessment report, and the way it was framed was by considering human influence in the future through radiative perturbations and a family of scenarios, radiative concentration pathways. And these scenarios were used to explore climate responses, here shown on a time scale of 3 centuries in the future. Looking at the long-term perspective is critical, I think. And these scenarios were also explored to assess emission pathways or mitigation pathways consistent with these radiative perturbations. And of course, there's a whole range of uncertainty, and this uncertainty arises from the implementation of forcings, especially aerosols in climate models. It arises from uncertainty on climate feedbacks, uncertainty or model spread, I would say, and transient climate response and climate sensitivity, especially from processes associated from the representation of clouds, and from uncertainty on carbon cycle feedbacks. And we have to carefully assess these uncertainties, especially when looking at subtle differences between implications of 1.5 degree or 2 degree. What was available at the time of AR5 were CMIPS projections, and they are summarized here, looking at 30-year running averages for 3 of the scenarios. The 2.6 scenario, that's compatible with less than 2 degree stabilization for many of the simulations, the 4.5 simulations, and the business as usual 8.5 simulations. And now let's look at the 1.5 degree target. And you can see that we have only a few of the simulations that could be considered as outliers, the models with the weakest transient responses that can allow us to explore a stabilization pathway. For the other options, it is to consider when 1.5 degree is reached in a transient simulation that goes above that level, and then focus on this time scale to assess what are the transient consequences. But this differs from a full coherent stabilization pathway. So we need larger ensembles. The HappyMIP project will be a contribution on time for the special report. We need to explore the transient climate response. We need the development of new SSP scenarios that will only be available for the full AR6 report. And we need also to fully address the dependence of regional climate response on mitigation pathways considering aerosols and land use. So now let's go to the climate response. What was known at the time of the AR5? It is well known that at the scale of the end of this century, regional temperature change can be scaled to the global temperature change. This is reported as regional degree of change per global degree of change. And there's new knowledge emerging on nonlinear increase, for instance, in hot extremes between today, 1.5 and 2 degrees. And nonlinearities are extremely important when looking at impacts, because there's an aspiration to make an interpolation between observed impacts today and those anticipated for higher levels of warming. Fully accounting for nonlinearities is really important there. Precipitation also scales regionally to the amount of global warming, but many of the changes here are at the limit of robustness or significance. And there's new knowledge emerging on significant differences in specific regions, such as the Mediterranean area, for changes in the hydrological cycle between 1.5 and 2 degrees. And these aspects will be covered in more depth by the 2 coming presentations by Richard and Sonia. I will skip that. Ocean acidification will, of course, depend on the greenhouse gas and CO2 emission pathway. And there's also new knowledge emerging, stressing higher risks than known at the time of the AR5 for some ecosystems and associated services such as warm water corals, bivalves, or finfish fisheries for less than 2 degree global warming. Sea level also is related to the amount of global warming, but we don't have yet enough information on how sea level change is related to the pattern of warming, the time above a given temperature threshold, especially with respect to the dynamical response of ice sheets. So there's growing knowledge on risks associated with Antarctic ice sheet dynamical instability, but for high-end scenarios, 3 degree warming or more. Little knowledge for lower-end scenarios. We don't have yet precise knowledge on the fate of glaciers for a given global warming target, for Arctic and Antarctic sea ice. Antarctic sea ice is a delicate point, because the response time means that we can't learn from transient simulations what are implications for the long-term response of the Antarctic sea ice and potential irreversibilities. We don't know much about permafrost carbon feedbacks for these low carbon emission pathways. And considering the most vulnerable countries, having in mind where the 1.5 degree invitation comes from, we need to know more about risks associated with cyclones and storm surges for 1.5 or 2 degree warming. Sea level is also a concern on the long term, and the IPCC report stressed the fact that there's a nonlinear response on the multi-millennial sea level commitment as a function of global warming. And this nonlinearity comes from thresholds for deglaciation of Greenland and sustained deglaciation on the long term. But you can also see here that we can also learn from the past, and this finding is consistent with information from the last interglacial period. The last time global warming was about 1.5 degrees above present day for a different reason and with different regional patterns than when caused by greenhouse gas forcing. We can also see the Pliocene information that is highly relevant, but with so large error bars today that it's not sufficient to reduce uncertainties. What do we know about potential abrupt change? There's one study that investigated a catalogue of abrupt shifts in CMIPS 5 climate model projections, and they had 4 categories of shifts: switches, forced switches, gradual change, and abrupt change, and related to different components. What is striking here is that a number of models depict abrupt shifts, especially around Antarctica, around the Arctic, and for snow cover in Tibet for small amounts of warming. That's illustrated here in yellow, between 1 and 2 degree warming. And we need to explore that further to assess how confident we are, or what is the credibility of these models with respect to the likelihood of abrupt change. Finally, the question about 1.5 or 2 degree warming is also a question about rates of changes and rates of changes for mitigation pathways. And you can clearly see that pathways compatible with at least 50% chance keeping global warming to less than 2 degrees, compatible with INDCs expressed during COP21 associated with the Paris Agreement, imply sharp decrease in emissions after 2030 and large amounts of negative emissions before the mid of this century, in fact. So these raises other questions for Earth system responses. How would overshoots affect Earth system responses? What are the biophysical implications and limits of negative emission options? So finally, this is the classical IPCC approach: working group 1, working group 2, working group 3, pathways on one side, impacts on the other side. And the benefit of this invitation for the 1.5 degree special report is that it's an opportunity to think differently, to integrate across disciplines and working groups early in the AR6 cycle. It has a lot to do with issues related to rates of changes and regional dimensions, especially for the most vulnerable ecosystems, countries, areas, and people. There's a very short time frame for new research to be published in time for the special report, so rates of change are also a challenge for scientists, I must say. And it's an incremental process. Not everything will be covered in the special report, but I wish that the methodologies, the new findings that will be developed for the special report will provide a basis for further assessment in the main assessment report by 2021-2022. And that's the end. Thank you very much.